Yes, so as Robert mentioned, we're going to talk today about building an end-to-end pipeline with Bert, Tensorflow, and Amazon SageMaker. So we're basically showing you how you can do data science specifically on the use case of NLP on AWS. So Robert mentioned it, and Chris was putting the links here eagerly in the chat window. So just a quick note here, and I have the website open. Chris and I are currently writing the book, the Riley book, Data Science on AWS. We do have an early release available on the Riley platform, and the final publication is currently scoped for early 2021. So if anyone is interested, you can find it. Just really go to our website here, datascienceonaws.com, and we do have, let me zoom in, we do have the links here on the top right. So you find the link to our early release. You also find a link to workshops we're running once a month. So we're going through all of the content basically in an extensive hands-on workshop. We just had it last Saturday, so the next one is coming up in September. And we also do have the link to our GitHub repo in here and to the recorded talks we're doing. So yeah, scrolling here and introduced myself, developer behind machine learning, and similar Chris. And yeah, so a lot of talks we're doing. And if you follow here the link to the book, you will come to our early release on the O'Reilly platform. And you will also find the link to the GitHub repo. And this is going to be more interesting for today. So if you follow that link, for example, and you scroll all the way down, you find a workshop agenda. And I just zoom in here as well. And this is basically also the outline for today. So quick housekeeping, how this is going to work. I saw we had a couple of questions here coming in already. If there's some hands-on live parts today. We do have a lot of content here as part of this workshop. And what we're going to do today, because we just have 2 hours with you, I'm going to walk you through kind of the main sections here. So I'm going to quickly show how you can get your data into F3. Then I'm going to walk you through a little bit of data exploration. We're going to use some ad hoc queries on the data in F3. We're going to visualize a little bit the data set in the notebooks. And then we're going to also start preparing the data for our NLP use case. And just a quick hint here. So we're using the Amazon customer reviews data set. So if you're not familiar with that, it's a published data set from Amazon that contains more than 150 million customer reviews from the marketplace. So it's a great data set if you want to start exploring NLP and yeah, playing around with it. And this is the data set we're using today. So we're going to prepare it a little bit, preparing it to actually create the Bert embeddings we're going to need. And also as a framework, we're going to mainly use TensorFlow in this workshop and also today. And then you can basically prepare the data, and then we're training. And to be more concrete, we're going to fine tune our Bert model. We're going to use, and Chris already gave out the spoiler, we're also going to use the Hack library. So this is going to be the pre-trained formal library we're using to analyze our input data and also just
academic.
And maybe just if everyone could go on mute if you don't have any question, that I think helps. Thank you. All right, and then once we trained, we're going to optimize and then show how to deploy. All right, let me just quickly see. I think everyone is muted here, so I can see, right? Okay, good. Sorry. Just trying to reduce the background noise here. All right. So this is going to be the outline for today. As I said, in the workshop, we're running once a month. We're normally doing this with a hands-on for everyone. Today, it's going to be a little bit busy for the just 2 hours, but feel free to look at the code and reproduce if you have access to AWS accounts. And for today, really just join me while I'll show you how the setup works. All right, and with that, let's get started. What I've here is basically, I'm in the Sagemaker environment, which is Amazon's AWS hosted and managed machine learning service, which gives you a lot of capabilities to really start building, training, and deploying your machine learning models. And in here, one part of the platform is also hosted Jupyter Notebooks. And in here, I just created a demo environment, which I can use throughout the demo parts. Basically, this is what I open here. So let me jump in my Jupyter environment. And this is exactly the same outline as you've seen in the GitHub repo. So I basically just cloned this Git repo into my Jupyter environment here. All right. And let's start here with data ingest. So what we're doing in the data ingest part is really just get our data set into S3 to be able to further process it with the tools and services. And let me open the next notebook as well here. See, the network is a little bit slow. This one is up. All right, so the first step is really, as I said, we're using the customer reviews data set. Let's have a quick look. It's public available, so you can just go Google that, and here's an introduction to the data set, how you can actually pull it down and work with the data. And just to have a look how the data looks like, it's consisting of a couple of columns. It's provided in TSV and per K data. And it's basically containing marketplace information, which is, for example, the Amazon.com marketplace in the US, or it also has German, the UK marketplace. I think French is in there as well. So you also have some multilingual data. And the review ID, a randomized customer, product ID, etc. So a lot of information. And the ones we're primarily in is the star rating. So whenever a customer provides a review, a 5-star or 1-star rating. And let me just make sure once more.
Yeah, Antje, there's one person that's unmuted. Toby, can you mute yourself? Yeah, unfortunately, Antje, you are the only host right now because of the way Robert handed things over to you. So we can't mute from our side.
All right, so that's the data set we're going to use, and we're going to have a quick peek into that also to see how the data actually looks like. All right, so the first part in this section is really have a quick look, and here you can see I'm just listing the files that are available. So exactly, here are the multilingual files from the different marketplaces. You can see Germany, France, Japan, UK, US. And then for the US ones, it's basically broken down into categories. So those are the product categories that are available on the Amazon.com marketplace. So obviously books, it's actually the most reviews that are part of this collection. And it's a collection from 1995 up to 2015. So you have a good amount of review data in here. And really, yeah, across all of the different categories, kitchen, lawn and garden, shoes, software, etc. All right, so what we're doing is basically we're simulating an application that would normally in a use case write data to an S3 bucket, to a data lake. And to do that, we're basically really just copying the data from this external bucket into our private S3 bucket, which I set up here in my account, just to kind of simulate the data lake. All right, that's pretty straightforward. So you're basically just running a copy command. So if you're familiar with AWS, that shouldn't be too surprising if you haven't seen it before. It's literally kind of saying I'm using a CLI command here in F3, copy source path into my destination path. And what I'm going to do here, I'm just pulling down 2 categories with the reviews, so that the actual jobs here complete in time. You can obviously run this on the whole data set with 115 million reviews. It might take a little bit longer for the training jobs, etc., but you can definitely do that. All right, that's just really quick on how you can get the data into S3, into AWS. And then what we're also using here in this chapter is a service called Amazon Athena. And Athena helps you to run queries on the data in S3 without even moving it anywhere. And this is particularly helpful if you just want to quickly explore the data, check how the data looks, if there's any reasons you might need for your machine learning use case to enrich it with other data, etc., how the features look like. So what we're doing here is setting up a connection to the service. And we're doing this by a tool called PyAthena, which is basically just a Python client to connect to that service. And then in order to run SQL queries on the data, you need to kind of define the schema, the metadata. So in this case, we're creating a database name and a table, and that is stored in a data catalog service, which is another service from AWS, which we're using. And once you've set up that schema, then we can actually tell the service to connect to S3. And I'm gonna use the term kind of register data and connect because we're not physically moving any data. So this is really powerful. And for those of you who are interested, actually Athena is based upon Presto, which is an open source project which is dedicated to exactly do that, run queries on a large set of data without having the need to move it. So once this is set up, we're basically defining the table structure here again, and then we can start issuing SQL commands. So here I'm creating a create external table if not exists, passing in this schema information, how my data set looks like. And once I have the table, I can then connect and run SQL queries. So a simple one here, select star from, it's the hello world of SQL, from my table where the product category equals digital software. And I'm executing this through the PyAthena setup. And I can pull the results here in a data frame in my notebook. And here we go. So here you can see how the data looks, right? So marketplace, in this case, it's US. Some random custom ID, don't worry, it's not your real custom ID. Some review ID, product IDs, etc. And as I was pulling down the digital software, you can see here that the reviews show up. For example, Norton Internet Security User actually got a star rating of a 5. And the title is Works as Expected, and the same for the review text. And you also have the review date when the review was posted. All right, I think pretty straightforward in terms of how the data set looks like. Perfect. So once we have that in place, you can also do some things. You can use Athena, for example, if you need to convert your TSV data, for example, into Parquet. So Parquet is really useful once you do data analytics. When you run, for example, SQL queries on a large group of data and you want to, for example, use filters like where product category equals. So you're basically querying based on columns, and Parquet is exactly optimized for that purpose. So it's a columnar optimized format, a binary format. In most cases for machine learning, we're working with row-based, and that's why moving forward, we will work here mainly with the TSV data. All right, one tool I want to quickly show you before I move on here is Aws Data Wrangler. It's an open source project coming out of AWS, which extends the power of pandas really to AWS and helps you to kind of, as the name says, wrangle the data across a couple of different services, and you can easily pull that into a data frame. So if you're working inside of AWS and with those services already, have a look. This is coming in handy. Here we have a couple of examples. For example, if I do a query, and here I'm using the Parquet data, I can use Data Wrangler to read Parquet from S3. I can select the columns I want to have, and I can use push down filters In this case, product category equals digital software. And this pulls the results straight into my pandas data frame. And here I do have the results. And there's a lot of more integrations with other services and also really, really good capabilities in terms of optimizing queries. For example, you can read results in chunks, which is helping to really be memory friendly with larger data sets. So in this case, if you enable chunks, it would return a new data frame for every file in the data path. And for example, if we pull in the whole data set, we would probably have around 60 TSV files. So if I use this chunk, it would return one pandas data frame per file. All right, this is really just a quick side note here. And with that, let's jump into the next section. So we have the data ready. And I want to also show you how you can explore the data. And let me open up this notebook here. So once we have the data available in S3, and we also have registered it with Athena, we can actually run and visualize some queries. So let's understand the data a little bit better. So what we're doing here in the Explorer is again using the connection with PyAthena, but now we're also pulling in here matplotlib, etc., setting some seaborn parameters, and we want to run some queries. A little bit of helper code I've developed. So for example, which product categories are the highest rated by average rating? And here you can see that's the SQL query for that purpose. And also you would run this with a PyAthena connection. And I just see this one I haven't saved before, so let me quickly run this actually. So to actually see the visualizations coming up here. We also included a couple of examples here that are run on the whole data set. So we can actually see the results that are even more interesting. So here are the SQL queries for the first one. And in this example, you can see digital video games has an average rating of 3.8 and digital software has an average rating of 3.5. So it's actually not the most highest rated categories in the data set. And you can start visualizing that. So the first one here always explodes a little bit in size. But even more interesting, that's why I scroll down here, is if you run those queries against the whole data set, you not only get those really, really rainbow colored nice visualizations, but you can also see a little bit better and understand the data better. So here you can see that gift card is actually the highest rated product category with 4.73, which I guess, yeah, everyone likes gift cards, right? And if you scroll down here, it's followed by music purchase, music, books, and all the way down, yeah, digital software. It's indeed the lowest rated category. All right, you can issue a couple of more queries here, which product categories have the most reviews. So you basically slice and dice the data set and try to understand it better. Here we can see digital video games have 145,000 reviews, digital software 102,000. All right. And we can visualize again here, and again, more interesting against the whole data set. So here you can see the number of ratings, and books have definitely most reviews. And if I scroll down here to the axis, you can see this is close to 20 million. So close to 20 million book reviews, and also followed closely by digital ebooks. And I guess this is also pretty understandable and explainable. Books have been the first category on Amazon.com, right, when they launched. So a long time to provide reviews. And digital ebooks actually, yeah, are coming close. And then it drops dramatically right here. And I guess personal care appliances, they have under 100,000 reviews here. So yeah, big drop in number of reviews. All right, and you can do some more interesting engineering, and you can ask questions like, when did the product category become available, each of them? And this is not scientific, but you can roughly guess by the date of the first review in that category. So this is what we're doing here. We haven't checked if this is really a solid assumption, but let's just look for the first review that appeared. And this we just assume is roughly when the product category got introduced. So you always see the SQL command, and I guess the visualizations are more interesting. For video games, it was in 2006, and for digital software in 2008. Scrolling down here. So visualizing, it's not too interesting with the two categories only. You can see here. But again, if you plot this for the whole data set, you can see a really nice chart here. And you can see that in, I think it's 1999, there seemed to be 30 new product categories which got introduced. So again, this could be just the data set or actually reality. We would have to check actually to see. All right. So we can run a couple of more questions and a little bit of more visualizations. Actually, I have a lot of code here just to plot this stacked percentage bar chart where you can see the distributions of the 5, 4, 3, 2, 1 star ratings per category. And again, if you're doing this across the data set, it's coming up with this nice visual. All right, I'm scrolling down. We have a lot of things in here. One is also maybe interesting, the distribution of star ratings. So if you check for the whole data set, the number of reviews per star rating, you can see that there's way more 5-star ratings than there's ever a 2-star rating. And I guess also explainable. So humans tend to give reviews when they're super excited about something. And they tend to take the time to write a review less or fewer times when there's just, you know, the product is okay. I would have expected though that the 1-star ratings, maybe they're also maybe higher, but all right. So this is kind of the distribution. And then you can check for the average star rating over time, for example. So there was a drop in those two categories. I think that's when software got introduced. That pulled the average down here. Oh, why? If you run this across the whole data set here, you can see this line. So there was a bit going down here, a little bit recovery and down and then up again. And remember, this is just up to 2015, the data set. All right, going down. If you plot it for each and every category, it's this busy chart, and you can definitely detect some outliers here, right? So some categories really had drops in 98, in 2001, 2008, 2010 here. So if that's, you know, your business, you would want to have a look what happened here. All right, and then I just go maybe to one of the last ones. So we're getting into the NLP business here. So one of a fun question we try to see is how we can check for anomalies. And we thought, well, what would be an anomaly in this data set, right? And we thought, well, maybe if one customer is rating the same product more than once. So we tried to gather that information here. And if you're interested, here's the SQL query. And if we're running this for just the two categories we have, we see that video games, Call of Duty, there was a single unique customer that rated this game 10 times with a 5.0. So a big fan of Call of Duty. And if you run this across the whole data set, it's getting more, more interesting. So there is one unique customer that watched the DVD of Pearl Harbor apparently 130 times and still gave it a rating of 4.2. And I have to admit, I watched Pearl Harbor, I guess, 6 times, maybe 7 times, including on TV. But yeah, I mean, 130 times is definitely a record. And then the second one is also interesting. So somebody watched Shania Twain live in Chicago 110 times. And do I remember this correctly, Chris? Aren't you a big fan of Shania Twain?
Big fan, big country fan. And I'm from Chicago.
Wow. That can be true.
It's a bit suspicious.
Bit suspicious, a lot. So maybe we just identified that random custom ID here. Good job. So coming back to the NLP discussion, I think that's what most people are interested in today. So one step we were doing here in preparation for to train the Bert model is actually to understand the distribution of our reviews. and especially the length of the reviews. So if you've played around with NLP models, with Bert already, there's we call it a hyperparameter, actually, the max sequence length. So the maximum length of the tokens. And you want to kind of figure out which parameter, which value to set it on, right? Is it better to set it to 128? Are you using 64? Shall we use 256? And so we can actually calculate that. So we're running a query here where we're taking our review text and we're splitting it by white space. So we're basically splitting every word. So this is not yet the tokens, but words is coming close enough for this approximation. So we're counting basically the words with a cardinality here from the reviews. And then we're gonna visualize them. And we're also gonna describe the percentiles so we understand our reviews better. And I guess the visual here is explaining that the best. So let me zoom in here. So this is basically the number of words. And we can see here the distribution that, yeah, maybe the maximum. Let me see, that is kind of funny. The maximum is 5,347 words of one review, I guess. And there's also the minimum is a single word, which probably is more often than just once, like a great, a perfect, right? But looking at the distribution, we can see that with 70% of our reviews are 59 words and less. So plotting this here, you can see it, right? So, and if we select a max sequence length of like to the powers of 2, 64 is coming pretty close here to the 70%, right? So depending on your data, you might choose to go for 80% coverage or maybe 90%. In our case, we really try to optimize here, not to go for a too high value. We were looking at 128 before, but then we plotted it and saw, well, this is really kind of the long tail here, right? So 70% should be good enough for our use case. Hence, we're going to choose 64 as our max sequence length in the next section when we prepare the data. All right, so this was kind of the lead into the next section here. All right, so let me switch back here. And oh yeah, one more thing. So let me open this one. And just as another side note, so we were exploring the data now pretty much in the notebook, right, with the visualization. We ran the queries on the cloud, on the data in S3, but we visualized with Matplotlib and Seaborn basically in our notebook. And I want to show you here another interesting project. And while my notebook is loading, I guess Europe is starting here to watch Netflix. Let me pull up here DQ. So DQ is another open source project which is built on top of Spark to run what they call unit tests for data. And using DQ, you can basically measure data quality in your data sets. So this is really interesting. So leveraging Spark, and you can then define specific data constraints. And I think here we go. All right. So let me just make sure this is loading correctly here. All right, so what you can do here is running DQ inside basically a concept coming from AWS. So part of the SageMaker platform is a service or like a functionality called processing jobs. And you can use processing jobs to execute a script and do processing on your data, as the name says. So how that works, it's basically mapping an S3 bucket for your input data right into a container, which will execute your code. And it also maps another S3 bucket here for any data it's writing out. And we're going to use this concept of this processing job to basically run DQ on Spark. So it's kind of a serverless Spark. We don't need any EMR or any other setup. Really spinning up Spark inside across a couple of those nodes. So it's kind of a distributed way to run this data analysis. And I'll quickly show you here how that works. That's again our data set. So here's the columns. What we're doing here, and this is really kind of a very customized approach. So we're bringing our own image. In this case, we're building a Spark Docker image to run. And you can basically see here, I'm not going into much details because we have a lot more to cover. But if you're interested here, you can see the Docker file. So we're pulling in here, installing Hadoop, installing Spark. And then we can basically build the container and push it to a registry. Here you can check that it's working correctly. We're pushing this to a Docker repo. In this case, we're using the Amazon service ECR. And next, we really just need to develop the script, which is actually running those quality checks using DQ. So here's the script that we're using. Here we go, the Scala script. So yeah, DQ uses Scala. So we need to kind of do a little bit of shimming here to get it into Python. But basically, DQ uses Scala. So we can see here, we're defining our data structure. Those again are the columns of the data set: marketplace, custom ID, etc. And then we're reading in the data, simply here, CSV F3 input data. And next we can define what we want to analyze. And here you can see, so we're gonna read in the data set. We're gonna calculate the size of the data set. That's the total size. And then we're gonna check for review ID if it's complete. So we're gonna check if there's missing entries. And on the review ID, we're gonna do an approximate count distinct, just to get an understanding of how many review IDs are there. And the approximate count distinct uses a hyperlog lock, which is more efficient than doing the distinct count. We're calculating the mean of the star rating. We're checking that the top star ratings are larger than and equal 4. And we're also checking if there's a correlation between the total votes and the star rating of a review, and the total votes and the number of helpful votes. So doing a couple of checks, you can customize as you like, depending on your data set. And then basically we can define specific constraints to check against. So for example, once we have the size, we want to check as a constraint that we have at least 200,000 rows in our data, that the star rating doesn't suddenly show up with a value that should not be in there, right? Like a 0 or a 6. So we're checking that star rating has as a minimum a 1 and as a maximum a 5. We check that the review ID is complete, meaning there's no null in there. It's a unique value, that's another constraint. We check that marketplace is never null. And we can, for example, also check that it is contained in an array using those marketplaces we know it should be in: US, UK, DE for Germany, Japan, and France. And then we run the job. And we're saving the metrics, etc. So we're using this processing job capability from SageMaker to execute this on the data set. So here again, we're giving it a job name, we're passing in our image and running that command in the Docker container. And we can specify to do this in a distributed manner. So here we specifying the cloud instance type we're using and the number of instances. In this case, we're running it across 2 nodes. And let me scroll down here. So we're starting the job here, pointing to our script. So here's the little shim code that puts our Scala code into Python. And once the job is complete, I just scroll all the way down. So we see quick results. So we can analyze the constraint checks then, right? And here you can see that pretty much all of those constraints returned a success. So that's good. So our data is okay to move forward. And we can also see here the exact outcome. So we can see a review ID complete. 1 means it's complete. We can see the approximate count distinct for review ID. It's roughly 238,000, looks good. We can see that total vote star rating are not correlated. It's even negatively correlated. We can see the total size of the data set, 247,000. Star rating, the mean is 3.7, etc. Right? So pretty much that's the data analysis part. And you can also develop your own constraints, right? So it's a great way to check if your data is really in good quality, in good shape to start preparing and training your model. And it also suggests new constraints. So for example, here it suggests for a verified purchase check. And it identified that the verified purchase has value range yes and no. And here's basically the code you can just go ahead then and copy paste and add to your script. All right, so that was another way to do data quality checks at scale using a project called DQ. Super exciting. All right, so that was Ingest and Explore. Let's now start with preparation. So let me pull up this one here, think straight. And apologize here, I think there's a lot of traffic going on in Europe right now in the evening hours. All right, so the next step now that we check that our data is in good quality, we start with a feature transformation. And again, we want to build a model that is based on Bert, and we want to provide review text, and we want to have the model classify the correct star rating. So when I send the model, maybe I love this product, I use it every day, I want to have the model saying that's a 5-star rating, right? So in order for us to do that and to prepare the data set, we have to do a couple of steps. So first of all, the raw data consists of a star rating, which is basically our label, and the actual review text, like this is a great product, not a good product, wonderful, whatever. And for Bert to recognize and to work with the data, we have to first transform it into Bert embeddings. So this is going to be our transformation step. And as we're using TensorFlow, we also gonna transform the training data into TF record. So TF record is just an optimized file format, also binary to leverage within TensorFlow training. So those are the two steps we're gonna do. And you're gonna see here that once we transform the data, the raw review text, it's gonna show up as those basically vectors or numbers here in the reviews. Whoop. I scrolled too much, sorry. All right. So let's see how that works. So we're setting up the environment here, and this is really kind of to interact with the AWS cloud. We're setting up where to find the data. So this is our S3 bucket, which holds the TSV data. This is our raw data. We keep using those, just the two files, so the jobs don't run too long, so digital software and digital video games. And we use another script here. And let me just open this up. So what we're going to use here is a script for the pre-processing. And we're pulling in here a couple of scikit-learn libraries, pandas obviously, pulling in TensorFlow. And here you can see that we're also using Hugging Face. So we're not training the Bert model from scratch. So we're going to leverage a pre-trained model transformer from Hugging Face. And for those of you not sure if everyone has yet worked with Hugging Face, probably Chris can also put in the link. And I guess in the meetup, you had a couple of sessions, including Hugging Face. It's really, really a very popular library here for transformers and super easy to work with. And we're also going to use those transformers here. And I think, yeah, they have close to 33,000 GitHub stars. So really kind of a popular library here to work with the state-of-the-art NLP models. It's supporting PyTorch and TensorFlow. So exactly what we need. All right, so what we're going to do here, you can use the pre-trained Bert model, and in this case, we're using DistillBert, also as a tokenizer to transform the raw text, the words, into the Bert tokens and embeddings. So this is what we're going to do here. So from this DistillBert tokenizer, which we're loading from Hugging Face, the DistillBert Bert uncased, that tokenizer, we're using them in the next steps. We're also specifying we're interested in the review body, which contains the actual text. And our label column is the star rating. And again, we have values from 1 to 5. All right, so we're reading in the input features. And then we do have here the convert input. So we're using the tokenizer to tokenize our input text that we're reading in. And those are the tokens. And then we are gonna encode them. So depending on the max sequence length, and here you can see that, we're passing in that parameter. So let's say in this case, we're using 64. And if you have a review coming in that has more than 64 words, it's gonna get truncated. And if you have less, it's gonna get padded. So we're setting here pad to max length true. All right, and then we're setting up a couple of more parameters that Bert is expecting. So the input IDs are basically then the indexes, the numbers of those tokens in the Bert vocabulary. So Bert, I think, has up to 30,000 entries in the vocabulary, 30,000 dimensions. So this is going to be the input ID. The mask will then say if there's a 0 or 1, so 1 if there's a value. And in case you have padding, those will be masked with a 0. Segment IDs, we don't need. This is more for question answering and next sentence prediction. And the label ID is basically the idea. So ID 0 would be the label 1, so star rating 1, and yeah, etc. All right, so we're going to calculate and return then the features we calculate. And as a next step, we're also converting features to TF record. So here we're using the TensorFlow capabilities to basically write the output file as TF records. All right, so a little bit more of parsing going on. So those parameters which you see here are a little bit more specific to the Sagemaker environment. So here, for example, if we're running this distributed, so we are running maybe 2 or 4 instances that will process the data, we can parse in this argument host, and this will give us a list of all of those hosts that are running the job. So in case you want to work with that information, you can pull in the current host, etc. And we're also setting here the arguments to keep track of the train split percentage, validation split percentage, etc. All right, so we're also going to transform here, as I said, the TSV to the TF record files. And we also do have a setting here to balance the data. And yeah, so a lot of code which we're doing here then. And here actually we're calling this then convert and features to TF record process. All right, so this is our pre-processing script. And we're setting this up the same way that I quickly showed you the DQ capability. So we're going to reuse the processing job again for us to run this pre-processing script. And again, we're setting a couple of parameters here, like which instance type in the cloud we want to run this on. Here we're just picking, which is called MLC5. So this is a compute optimized node. And we're going to run it on 2 of them. And we're setting parameters how to do our training, validation and test data split. So let's do 90% for training data, and let's split the remaining 10% in 5 for validation and 5 for test. We're going to balance the data set, and we're going to also set the max sequence length to 64. All right, and here again is a quick hint to why we're doing this. If you've seen that in the notebook before that I showed, we were running a query on our data set to check the distribution of how many words do our reviews have. And you can see pretty much that the long tail starts after 64. So in this case, and this maps to 70 percentiles. So with 70% of the data set has 59 words or less. So we're actually doing a good choice here, I guess, with 64. And in general, it's just a good common practice to select numbers to the power of 2. So we're going for 64 here. All right, so we can then use this processing job. In this case, there's a pre-built Docker image for scikit-learn. So in this case, we don't have to build our own Docker image, which we did for the Spark job. Here we can just really use a pre-built one, specify the framework version, passing in the permissions role that is needed for the cloud, passing the information instance types and counts. You can set a maximum runtime if you want to limit that. And then we're passing in here our Python pre-processing script. And we're also pointing the job to the input data. So again, this is an F3 bucket, and it's going to get mapped into a specific folder structure inside of the container, which is the opt.ml processing input data. And as we're going to basically split the data into training, validation, and test, it's going to get written out into 3 different folders. So those are the 3 output folders. So one called Bert train for the training data, one Bert validation for the remaining 5% validation, and one for Bert test, again with 5%. And here are the arguments which we set for how to do those splits, the max sequence length, and whether to balance the data. All right, and this is kicking off the job on AWS. So let me scroll down here. It's going to run for a little bit, processing, crunching the data. And once it's done, we can check the outputs. So we can see here that those folders got created in our F3 bucket. So we can see the output Bert train, the output Bert validation, and Bert test. And if we look into those, we can see here we do have the same 2 category files, but now here converted into TF record files, and obviously containing the Bert tokens. All right, so this is pretty much the pre-processing step. And with that, we can maybe show you quickly. We have one more notebook here which runs that in the actual Jupyter notebook here. And you can see the outputs here. So I just do that quickly. So this one was just running the same thing, but not on the cloud. Really just a quick sanity check in the notebook, which is good if you just want to quickly prototype and see that your code is working. You don't want to wait for the whole job to finish. You just want to, on a small subset of data, check if it's running. So this is what we've done here. And here we actually show the outputs. So here you can see if I pass in a couple of sample strings, I needed an antivirus application, and I know the quality of Norton products, etc. You can see here the tokens showing up. So it got split into I needed N, and it split the antivirus into actually 2 tokens. So the anti and then the virus. So it's basically creating those tokens using the Hugging Face tokenizer. And then you can see the input IDs, mapping those tokens to the Bert vocabulary. And then you can see the padding for anything that is below 64. So you will see all the zeros here being padded. And this maps exactly here to the input mask. So all of the indexes which have a value have 1, and the padding will have the zeros. Segment IDs we're not using in this case because we're not doing question answering. So this will show up as 0 here. And then the label ID is basically the star rating, right? So a 4 would map to the 5-star rating. All right, so that hopefully makes it a little bit more visual. Let me see. Yeah, we also print out a TF record if you're interested. It's a binary format, so you can't read too much. A little bit in between you see here is like segment IDs, but this is basically if you just print out a TF record. Not much what a human can do with it. But TensorFlow. All right, so let me close those 2. And with that, we're basically through ingest, explore, prepare. So next would be train the model. So I'm going to jump here into the training section. And let me pull up here this notebook. Also needs a second to come. Here we go. So now we're ready to start the training. And really, to be clear, we're not training Bert from scratch. That would probably run many, many hours, if not days, depending on the data and the availability of GPUs. What we're doing is we're really using a pre-trained Bert model, which we can easily get from, for example, Hugging Face, right? So that's what we're doing. So we're using a Hugging Face pre-trained DistillBert model. And maybe just a quick note, DistillBert, the name reflects that the model got trained with distillation, meaning it's a way to train a model by having a teacher model and a student model. And it really helps to be more resource efficient. So DistillBert maintains, I think, roughly 97% of the accuracy of the base BERT, but it's way more efficient in size, etc. So we're using that one. And then we also just showed how you can do the feature engineering. And what we're doing now is we're adding a classifier layer on top of the pre-trained model to basically adapt to our review data and also to tell it to do this classification of star rating. And this is what we're doing in this notebook. So we're pulling in, again, just a couple of settings to interact with the AWS environment. And we're also retrieving the location of our preprocessed data. So for the training data, the validation data, and the test data. We do have a couple of code checks in here just to make sure when we're running the workshop that those parameters are set correctly. And we're also using another capability here of Sagemaker, which is experiments. And with experiments, we're able to kind of track each step throughout this development cycle. So we're gonna track the inputs and the parameters of the prepare step, of the training step, the optimize step, and the deploy step. And just quickly, the concept of this experiment tracking. The experiment is kind of a collection of what we call trials. And you can add those trials to an experiment in order to compare them afterwards. And a trial is kind of a multi-step machine learning workflow, which contains, for example, the prepare, the train, the deploy, etc. And those steps are called the components. And then each component has a little tracker, which basically logs the information. So what we're doing here, we're creating a single experiment. And we're going to do a trial A, which can have two components, and you can spin up in trial B, for example, to have different components. And then you can compare, for example, trial A maybe had accuracy of 95%, whereas the trial B might have only, or might be better, even 97, etc. And then you can decide afterwards. So it's always good to keep track of what you're doing here, especially if you're running those experiments at scale. So we're creating here the experiment, we're creating the trial. Then we're creating a trial component called prepare. For this prepare step, we actually did in the notebook before. So we're just adding it in this step here. And we log all the parameters we had. And we specify the data set again, where to find our preprocessed data. So here again, we've seen this before. So this is our TF records for the training data, the validation, and the test data set. We can also optimize depending on the platform you're running it on. So for example, if you're working with AWS and S3 data, we can set here a distribution strategy called sharded by S3 key. And that means if I have more than one file, in this case, we have 2 files, basically 6 files, including the test and validation. So when I do 2 instances, which will train, and I do sharded by key, each instance will receive one of the 2 training files, for example. So it will be distributed equally around those instances. So it's a good optimization strategy to use. All right, then we're setting up hyperparameters. So we're building this neural network, and we're using the pre-trained Bert model as kind of the first layer, which is in itself like a very complex architecture. But then we're really attaching this classification layer on top. So for this classification layer, we need to set, again, hyperparameters. So one, we already know, that's easy, the max sequence length. We keep that to 64. And that's also a very important point. When you're building up those NLP models, those Bert models, you have to stick to the same max sequence length you're using in the preparation and the feature engineering to the same value when you're doing the training. So again, this is why we're treating this as a hyperparameter, and we keep logging it. So we're making sure that our whole pipeline is based on the same value. And then again, I'm defining here training parameters for my model. So for example, I want to run 5 epics. I set a learning rate to a value that I think might lead to good performance, epsilon value, the training batch size, validation batch size, etc., the training steps. You're probably familiar with that. Again, I'm choosing an instance type here. I just experimented before the meetup today. So I pulled in a GPU-based instance. So again, this is also the power if you're running that on the cloud. So you can pull in a GPU instance when you need to get a job done very quickly. So here I just used a GPU instance. I just chose one because the data set is not too large, but I wanted to have the job done quickly. I didn't want to wait 2 hours. So that's what I've done here. And also you can spin this up, right? If you want to scale, you basically put in here instance count 10, and then you're running distributed training across 10 nodes. So super easy. In this case, 1 was enough. Setting a couple of more parameters. And yeah, so another step is we want to keep track of the metrics during the model training to see the performance. And here you can see log lines that TensorFlow will emit. So for example, the loss and the accuracy. And we want to kind of grab those from the logs. And we can do this easily with, I think it's down here, with a metrics definition. So we can use a regex. It's a little bit crazy here, but you can use regex expressions to kind of grab those values from the logs that got printed basically during the training. So we're setting this up to keep track of those. So we're going to track for the training loss and accuracy and for the validation loss and accuracy. So we can compare those and add those to the experiment tracking, etc. if we want to. There's also capabilities to actually set up hooks during the training job itself. And it's based on rules. So it's basically a rule engine. It's called the Sagemaker Debugger functionality. And in here, we can leverage rules like, let me know when the loss is not decreasing anymore, right? So meaning, when are we starting to overfit? And we can check for others like, yeah, especially the overtraining here. So those are pre-built rules that you can just leverage. You can create your own custom rules as well. But we want to track here if that's happening, and then basically have a hook and tell us what's going on here. All right, again, we're setting checkpointing as well. So checkpointing is especially useful during longer training runs. For example, in AWS, you can use spot instances. If you heard of that, spot instances are making use of unused capacity in the cloud, and you can get those spot instances really in kind of a marketplace offering for a fraction of the normal cost. So you might have savings up to 70, 80, 90% of what the instance would normally cost just by using those instances from the spot market. But on the other side, AWS can reclaim those spot instances when they need it to fulfill customer demand. So they give you enough warning upfront before they take the spot instance back. But in that case, if you have enabled checkpointing of your training job, you can basically resume the training from an on-demand instance, which will get automatically provisioned once you lose basically one instance. So if the spot is gone, it will basically spin up an on-demand instance to continue your training job. And for that reason, it's really, really helpful if you have those checkpoints. So you can really pick up from the last checkpoint, resume, and not lose any time here in the training job overall. So we're also going to do that. Checkpointing is pretty much available. It depends on the framework, but TensorFlow supports it. PyTorch and MaxNet, so the popular ones support checkpointing. All right, and with that set up, we can start our training job. So again, for training, we provide here a training script. And here again, we're pulling in a couple of libraries we need. We're installing Hugging Face, transformers. We're installing the Sagemaker specific libraries. We're going to use TensorFlow to use a pre-built Docker image, which will execute this training job. And pulling in a couple of more scikit, matplot. And then from the transformers library, we're pulling in the Distilbert tokenizer. And we're pulling in the actual TF Distilbert for sequence classification transformer. A couple of TensorFlow Keras libraries as well. And then we start the training script. So we do have the classes, those are our star ratings. And we do select here the data and the label from the record. So we're reading in the TF records. And we're parsing here for the input ID, the input mask segment ID, and for the label. So we're basically splitting here into X and Y. And we do have here a function that is helping us read from the data set. So channel, input file name. We do have a setting that is called pipe mode. Pipe mode enables you to read the data and it streams into the instances that are running the training job. And that really helps also to kind of speed up the process, because otherwise you would have to copy the whole TF record file to the actual instance that is executing the training. With pipe mode, the instance opens up a channel to the F3 bucket and then streams the data as it needs to process it, so the training job can start quicker. So this is going to be set up here, reading in the hyperparameters, the values, the parameters which we set. Here we have name to features. So here we are basically setting those input IDs, input mask segment, label IDs. We decode the records. So here we're passing the TF record and applying those functions, loading checkpoint model if needed. And yeah, parsing in the arguments where to find the training data, validation test data, where the output directories, the hosts, etc. All of the information, the parameters we've been setting. So we have them available. And then we can start the training here. So a lot of code. Setting path. Also setting the distribution strategy for TensorFlow. So we're using, for example, TF distribute mirrored strategy in this case, because normally we're running this on a single GPU instance. So we're going to mirror that across all of the GPUs. All right, so we're setting up the training here, training data set, building that up. Checking for checkpointing again here, callback, optimizer, loss metric. And then finally, after a long time, we do the model compile. So here you can see how we're adding this classifier layer. So we're defining the loss. And in this case, we're pulling in from TensorFlow Keras the sparse categorical cross entropy. And as a metric, we're using Keras metrics sparse categorical accuracy. And with those, we can build up the model. And as optimizer, I think, where is it? I think we use Atom here. Yeah, here's the optimizer. We're using Atom. And this basically all together, and then we can start the model compile. And this will kick off here then the model fit, the actual training job. All right, a little bit more code here. We're also providing all of the information here the lauded model then ID to label, label to ID, which basically just does this mapping, right, from 0 to 1. And 1 could also be like could be a string and saying like star rating 1, star rating 2, etc. All right, and then we're also doing here in the log file tests straight away. And yeah, so this is the script. This was just the script. So I'm sorry for the scrolling. I just, yeah, pulled that here down again. So next, we're setting up an estimator for Sagemaker. So we're pulling in here the TensorFlow estimator object, and we're creating an entry point, which basically points to this training script now. You can specify a source directory, which contains the requirements txt file. If you have any additional requirements you want to pull in. An execution role, again, how many instances you want to run this on, what type. And we're setting here framework version, so we're using TensorFlow 2.1 in this case. We're passing all of those hyperparameters. And yeah, we're also creating another experiment trial component. And then we can call fit and start the training. And here we're pointing to the input data again and starting the training job, and it will run on the cloud. So after some time, when the training job is done, you can then check the trained model. So the model will be put in this output path as a model tar gz file. And you can see here everything that's getting pulled in. We even calculate the confusion metrics and pull that in as a PNG. So you can also see that if you like. And yeah, so you can use another CLI command from TensorFlow, saved model CLI, to actually see the model signature here. You can double check what inputs are expected in case you don't know. So you can see the input IDs are expected, the input mask segment IDs, as we know. All right, so looks like a valid TensorFlow model. We can also check the experiment tracking, and here we kind of print out so you can see what's happening. I was playing with the prepare, this is why it's called prepare 2, but basically you would add up all of the steps you're doing. So we prepared the data and now we trained the data, and you can see that here all of the parameters which you told it to store are basically stored. So there's way more now for the training than for the prepare. All right, so this is pretty much it. You can analyze those debugger rules as well, but I'll skip that for now. All right, so we do have a trained model now. Let me see. So I guess in the interest of time, I'm not going to do too much here. Maybe I'll show you quickly this notebook because it's really fun. If you have a TensorFlow model, which we do now, and you want to convert it maybe to PyTorch, there's a pretty neat trick you can apply to do this really, really quick. So I think, did this execute? Yeah, this shows the outputs. All right, so you can use also Hugging Face again. They're a real superstar to convert this TensorFlow model into a PyTorch model. So we're pulling in here the TensorFlow library and the Hugging Face transformer library. And now we're also pulling in PyTorch. And also, this is capabilities I'll show you in a bit. It's TorchServe, which is a new open source project to serve PyTorch model that AWS developed in partnership with Facebook. And we're going to use that as well quickly. All right, so with those, again, I'm querying here for my previous training job. I'll check where my model data lives. And then I can have a look again here into my model tar, which we already did. And I show you the really nice trick. So here we go. So we load transformers, again, Hugging Face transformers, import the Dilbert for sequence classification. And if you're familiar with Hugging Face, or if you paid very, very close attention to what I showed before, Hugging Face, as I said, supports PyTorch and TensorFlow, right? And the PyTorch versions always start just with a name. So this one, Dilbert for sequence classification. the TensorFlow version of it starts with TF, right? So we've been using the TF version before. And what I'm doing now, which is this little trick, is that I'm reading in, and you can see this here. So I'm doing the PyTorch Dilbert for sequence classification, and I'm calling from pre-trained, and I'm loading in my model. So this model is stored in this directory. And down here, I'm setting from TF true. So I'm loading from TensorFlow, and I'm putting it into the PyTorch version. So really, really cool. And this results in a PyTorch model. So here I have my loaded PyTorch model. So we just converted the trained TensorFlow into PyTorch. And at least I'm getting excited by that, as you can tell. So we can double check. We can run predictions here. So I just loaded it. And you can use a functionality called text classification pipeline, which comes from Hugging Face, to just test it. We're passing in this PyTorch model, the tokenizer, saying it's framework PyTorch, saying whether it's CPU, GPU. In this case, it's just my Jupyter Notebook, so it's definitely CPU. And I'm just using a string here. I loved it. I will recommend this to everyone. Passing this. And you can see here, label 5, score 1.0. It's pretty sure this is a 5-star rating. So the PyTorch model is doing predictions. Perfect. And we can save this out again here using save pre-trained. And this will give us the PyTorch model bin, which we then can use later to actually deploy it. All right, so this was just another quick side note here on how you can get to PyTorch the easy way. Yeah, maybe quick check with Chris here, as I was going pretty fast. So we are through the ingest, the explore, the feature engineering, and the training phase. And next, just quickly, I'm going to show you how to optimize hyperparameters, how to deploy, and how you can combine it in a pipeline. But maybe quick check with Chris if we have any maybe hotspot questions you want to address.
Yeah, as we see, like pretty much every time, there's lots of questions about the max sequence length. I think there's a little bit of confusion. So just to reiterate, you have the choice of the max sequence length. We did some analysis back in 05 Explore that showed that the 70th percentile of our reviews are below 64. You want to choose a power of 2. That's how Bert works. That's how modern hardware works. And if you go higher, you can go up to 512. That's a Bert limitation. That has nothing to do with Hugging Face. That's just how Bert was built. If you go higher, your training will take longer and will use more memory. And 64 was good enough for the 70th percentile to capture. So below 64, we were able to capture 70% of our reviews. So we went with that. Obviously, the larger the max sequence length, you will likely see higher accuracy, but training will potentially take longer. It will actually definitely take longer. And also you can go both directions for PyTorch and TensorFlow, and that's a feature of the Hugging Face library. So please thank Thomas Wolf next month. The PyTorch was actually the first implementation, and the next one was TensorFlow. So they actually just recently added TensorFlow, I think last year. We jumped on that right away. We had wanted to use Hugging Face, but we wanted to use TensorFlow to show the benefits of TF record and some other nice things like TensorBoard and the Sagemaker support for like TensorFlow as well. So. Yeah, so I think we are good. We're on. So did you show optimize yet, or you were just about to do that?
You show optimize and then deploy, and then you have a special that you also want to present. I know.
Yeah, the multi-arm bandit. Okay, awesome.
All right, perfect. So let's move on. So we do have another section here, which is basically, and I might show. Let me see the overview here. If it's loading all the pictures. There's one picture missing. Let me also open up the second one here right away. So once we have the model trained, there is another step, which is the hyperparameter optimization or the model tuning, right? So one thing is to really kind of train the model depending on the data set, figuring out all the parameters, but maybe you want to have some way to automatically look for the perfect set of hyperparameters, right? And this is something you can also do, for example, with Sagemaker. It offers an automatic model tuning capability. So what we're doing here is we're defining the hyperparameters which we're looking for. In this notebook, I'm going to use just the learning rate, but you can add as many as you want. And you have to define the objective metric, meaning what are you trying to optimize? In our case, we're going to pick the validation accuracy, and we want to maximize that. And then you can choose between a tuning strategy, and there are many, many ways to find a good set of hyperparameters. You could just do manual if you're working in the field for a long time and you build up a good intuition over time which ones to use. That might work for you very well. If you're a little bit newer or you don't have that much experience, you might want to look into some automated ways. And there's a couple of ways to do that. There's grid search. Grid search means I'm really kind of taking all of the hyperparameters and putting them together like in every possible combination. So I'm creating a grid of all of the combinations. And as you can tell, probably the algorithm will check each and every combination. And again, this might work well on just a few number of hyperparameters, but checking every combination, if you have like tens, hundreds of those parameters, maybe it will run forever, right? So another strategy is using random, which will pick randomly some combinations and try to figure out if there's any kind of the hotspot area where you see good results. Also, it's kind of maybe not that scientific if you just look randomly, although it's regarding research papers, it's doing pretty well. I feel better if I have a more like, focused approach. So there's another strategy called Bayesian. And here you're applying basically machine learning to a machine learning problem, which I think resonates very well. So with Bayesian, you're treating the problem as a regression problem. And that's why you're putting in this objective metric, which you're trying to optimize and to maximize in the case of accuracy. So this is what you can choose with, for example, also with the Sagemaker capabilities, you can choose between random or Bayesian. And really just quickly here, again, you specify where the data lives and you're using the same, in this case, we're using the same training script. Again, we're making sure we're using the same max sequence length. And then you basically define which parameters are static, which you just want to keep. Those are the ones we're pulling in here. And again, we're adding this to our experiment. We want to keep track. But then the next step is really to define this range of hyperparameters you want to automatically tune. And in this case, I'm just going for one, learning rate. Obviously, you want to probably put in a couple of more to play around with. But in this case, I'm really just going for the learning rate as an example. It's a continuous parameter, and I'm going to pass a minimum and a maximum. And I'm going to say, explore this range in a linear way. You could also put a logarithmic scale. Setting up again the metrics I want to keep track of. And then I'm creating this estimator object again. So this is the exact same setup as we've seen in training, right? So we're creating this object with a training script, any requirements, instance types, and those are the static hyperparameters. So that's my estimator object. Now I'm creating a hyperparameter tuner object where I'm passing in this estimator. I'm setting my objective metric to validation accuracy. It's type maximize. So in contrast, if I have a loss, I would minimize, obviously. Accuracy, I definitely want to maximize. And I'm passing in those parameters, the hyperparameter ranges, the dynamic ones. This is the learning rate. And the metrics I want to keep track of, and the strategy. So here I'm using Bayesian. And because I'm treating this as a regression, it makes sense that I have various jobs sequentially, because once one training and tuning job is done, I want to see the results, and I'm going to optimize the parameters for the next job. So here, just to be like a little bit shorter in execution time, I just do 2 jobs in total and 1 in parallel. So just 1 and then another 1. If you run this at larger scale, obviously you could do something like maybe 5 in parallel and do maybe 25 in total, or maybe 100 in total, right? Depending on how you want to treat this. All right, and then you can call fit on this tuner object, pointing to the data. And this will really start this tuning job in the background again on the cloud. So you're spinning this up against a couple of instances we defined above. And once the job is done, you can pull the results. So here we can see that learning rate doesn't really have too much influence on this example. So it just ran 2 jobs here and tried 2 combinations. And it didn't really have enough time to explore the ranges further, right? So you want to definitely have more parameters, and you also want to have more jobs running. But this is just really to quickly show how you can set this up. And then you can query for the best candidate, and then you can basically deploy the candidate or use that to further develop your model. All right, that's just quickly on the optimization. And now we want to deploy the model, right? So now is the exciting time when we actually put it into an environment to serve predictions. So let me open up this notebook here. So here we're going to deploy our TensorFlow model that we trained as a real-time endpoint. So let me maybe also quickly show up the overview here. And this might be my VPN. I might just try. Hopefully my Zoom stays up. Try this without the VPN if this is quicker. All right, here we go. And I think you can still hear me, right? Yep. All right, so here is a quick overview. So you have 2 ways to deploy a model into an environment. One way to deploy it is to an endpoint, to an HTTPS endpoint to serve real-time predictions. And by that, I mean, you're gonna deploy the model behind an API. And you can use that, in most cases, the REST API to implement and integrate in your applications. And then the applications can basically call the API for a prediction request, and the model will serve the request and send the response back, right? This is what I refer to as a real-time endpoint, because you spin it up and it's running there 24/7 and serving your applications with predictions. And it's really pretty easy. If you train the model on Sagemaker and you have this estimator object, you can pretty much just call deploy on that object and pass again the information, instance counts and type. Or if you have the model not trained on Sagemaker, you can also bring a model which you trained somewhere else, do a little bit of customization with parameters which Sagemaker needs. But basically you create a model object, and then you also call deploy on the model object, and you receive this predictor, and you can then call predict and pass in the data. So really, really easy. In general, and I kind of quickly skipped over that in the training section. In general, you have a couple of different levels of customization. So AWS and Sagemaker comes with a lot of built-in capabilities. So it also ships a couple of built-in algorithms, which you can just use out of the box. And they come with their own built-in Docker images. So Sagemaker will take the algorithm, take the data and the container and spin this up as train the model, and then use it also to spin up an endpoint. You can customize, and this is what I've been doing and showing here, by using your own script. You can write your own pre-processing script, your own training script, your own inference script, and still use a built-in container, let's say for TensorFlow or for PyTorch or MaxNet. Or you can go completely freestyle and customize, meaning you write your own code and you also bring a custom container, right? Maybe you have some requirements that you have specific libraries installed, etc., and a couple of more settings. So you can totally bring your own container and own code and also spin that up and just leverage really the scale and the flexibility of the cloud. All right. That's just, again, as a side note, the big second way to deploy a model is to do batch predictions. And here you really just point, have your data in a 3-bucket, and then start a batch transformation pointing to the data set. And the batch transformation job will spin up instances with the model you pointed to and run a batch prediction on that input data and write the results into a file. And then the instances get terminated, right? So it's not serving and spin up 24/7. So it's really just for doing the job. And then with the output data, you can decide what to do. All right. So quick look here how we can do this because Chris will show you something exciting today as well. Here's a quick way we're deploying our model as a real-time endpoint. So I'm pulling in again libraries. I'm looking at my model tar so I can untar and look what's in there. So this is the TensorFlow version. And I do have here again the saved model CLI, so I can sneak into there and check for the input types. You write an inference py, so this is the inference script. And here basically what you do is you define an input handler. And this is actually doing the exact same transformation. So when you send data to the model, you have to convert the raw text again into the Bert embeddings, the Bert tokens, also for the deployed endpoint, right? So this is the input handler, which is using, again, the tokenizer and transforming the live data that is coming in. Pretty much the same as in the training script. And you define an output handler, which again takes the result from the model and then passes this into a label maybe that you want to send back to the client. All right, and with that, I'm basically here creating this model object, passing the model name, where my tar file lives, framework version, and as I showed, I call the deploy, and this basically deploys an endpoint. I think I can click here, which takes me to the Sagemaker console, and then shows you here, for example, endpoints. I do have deployed a couple of endpoints today. Those are the real-time endpoints. And you can see here also, this is the API, which you can just grab and include in your applications, and it will start serving predictions for you. All right, that was pretty straightforward. You can simulate predictions here. So with this predictor, which I quickly showed, you can really just pass in sample text. So here I'm choosing, this is great, passing it into reviews and then showing the output. And here you can see the output is rating of 5. This is great. So yeah, did a good prediction in this case, right? And obviously you can also run this against larger data sets to check. All right, so this was quickly how to deploy a model. I also do have here a notebook that shows how to use the TorchServe environment. And I'm not going to do this, I guess, in detail because I want to give Chris a little bit of time. But basically here, to use this new library, if you're interested, if you're using PyTorch, have a look. It's an open source implementation that is helping you to serve PyTorch models. Really interesting. Comes with a management API, inference API. And basically you're taking your model tar and TorchServe or not the model tar, but the PyTorch model bin in that case. And TorchServe is expecting yet another format, which is a .mar, a model archive file. So the steps you have to do if you're interested is you're basically taking your PyTorch model, and then you have to transform that into a model archive file, a .mar. And this is really just what TorchServe expects. And you're setting up a couple of information, model name, where this model store is, and you're passing the actual PyTorch model. You're defining a handler, and the handler is basically, again, how to work with the data. And we do have one that is actually contributed also to work with Hugging Face transformers, so perfect. And then you're just providing some config information. And in our case, we're creating a Docker container to actually spin this up on SageMaker, but you could also just grab the SMAR file and then start torch serve and then have it serve the model. In this case, in this notebook, we're showing how you create a Docker container and then bring that basically as bring your own container to SageMaker and run it there and serve predictions. So this is really showing you how customizable the environment is. In this case, we're using torch serve here to host our PyTorch model. And yeah, there's a lot of code. I scroll through here. If you're interested, please have a look. And with that, I'll hand over to Chris. So Chris, is your notebook up and ready?
Yeah, sure is. I can't share my screen without you giving me permission, I think.
Oh, and I'm making you host right now.
Might log me out and log me back in or something, but.
No, it should seamlessly.
Okay. So a lot of great questions if you want to go through. Yeah, a lot of people know their stuff on this meetup, which is really good. So yeah, should I be able to share?
Of course.
Yeah. Go. Okay. So, and I believe you want me to show the multi-arm bandits, correct?
Of course. Exciting new content.
Yeah, I've been working on this for a couple weeks now. Okay. So let me show you a little bit about multi-arm bandits. Move this out of the way. Okay, so multi-arm bandits, form of reinforcement learning. And today we'll actually be doing contextual bandits, and contextual bandits mean we're passing in context to the multi-arm bandit to use to help it choose which action it should take. So one thing I do kind of uniquely when I describe multi-arm bandits is that I don't really use the reinforcement learning speak or terminology. I find it kind of gets in the way a little bit, and which was always like a mental blocker for me when I was trying to understand reinforcement learning. So I'm just going to talk to you in terms of models, and we have 3 models here. There's 2 TensorFlow models that have been trained the exact same way Antje showed. We trained model 1 for 1 hour. We trained model 2 for 5 hours. Model 2 has much better accuracy than model 1. What we're going to do is, and so I did that on purpose to show that the multi-arm bandit will learn that model 2 is the better model. And so there's a bit of a fabricated use case here where, you know, let's say you are putting in your review text to review something. Oh yeah, and then maybe Antje, can you send them the link to this 04 bandit model here in the chat? And all this code is all open source, all public. So let's say you type in the review text and click submit. Oh, and then you have to select the star rating also. And if we wanted to maybe detect if the review text didn't really match the star rating, you know, maybe this is something we could either flag sort of internally, or we would flag it to the user and say, hey, this doesn't seem to match. Can you double check? You know, it's a bit of a fabricated case, but just kind of work with me here. So the first step is to actually call into the multi-arm bandit. And the bandit will, in the beginning, just serve up both 1 and 2 sort of evenly, you know, 50-50, because it doesn't know which is the proper model or the best model for this use case. The bandit will then store this data into, here we are using S3. There's some Kinesis Firehose stuff that we choose to use just to scale this out. Yeah, don't worry too much about that. Just know that the data ends up in the S3. We get back this like unique ID for the event. That's what we'll use to actually track through this whole system. So once the bandit serves up either model 1 or model 2. Now the application calls that specific model 1 or model 2, whichever was served up. We get back the prediction. If the prediction matches, we then reward the multi-arm bandit. So again, this is a bit of a fabricated case here, but you can maybe like generalize this to your specific use case. So if the model 1 or model 2 predicted successfully, we then would send a reward of +1, and we are actually rewarding the multi-arm bandit to say, yes, you should be using this model, right? If the model does not predict it correctly, we send 0. Okay, we save all this, join all this data, and then we are continuously training with Sagemaker training job, just a typical training job. This is actually using Vocal Wabbit, which is a pretty good reinforcement learning library. We could also use Ray, we could use Coach, we could use Unity. These are all built in to Sagemaker. You can pull down those Docker images. They're all open source. You can look at them. You could deploy your own Docker image with your own reinforcement learning framework if you choose. And so just know that we are continuously training the multi-arm bandit, but we're still using the same trained TensorFlow models 1 and 2. So this is the overall architecture. Just wanted to kind of get this out of the way. And in technical reinforcement learning speak, the state, which is the context here, would be the actual review that we are going to predict. So that's why we see the review body getting passed in here and stored with the events. Then the multi-arm bandit will use that state to serve up the action. And here the action is model 1 or model 2. And then of course reward, which is typical reinforcement learning speak. So sticking with it there. Okay, and so this is actually open source code. You can find this right in this repo. It's under 09 deploy. And I think there's a link to it right down here also. You can click on that. That'll take you directly to this open source code provided by Amazon Labs. And what the goal here is to slowly shift traffic to the winning model. So a typical, just like straightforward, with a test where it's just doing A and B, right? A traditional like A/B test is fixed and static and will send 10% traffic or 50% traffic to A and then 50% to B maybe. If that model, if the second model B, right, is bad, or if like model 1 is bad, you have to run that experiment for the entire, right, if it's 2 weeks or maybe 1 month or 4 days, 5 days, whatever. So that's the key difference is with multi-arm bandits, we can dynamically shift the traffic throughout the life cycle of the experiment, which really helps to minimize regret, which is what we could have achieved if we were like dynamically shifting the traffic. So think of the bandit, which is kind of slang term for a slot machine. If we have 2 slot machines and so let's say the second one here, model 2 or slot machine 2 starts to pay out more, we want to start to exploit that particular arm, it's called. And so we would start pulling that slot machine more. And so so in like this domain, what we would be doing was sending more predictions to model 2. All right, so let's get to the code. Now, the Vocal Wabbit code is basically hidden from us. We don't really need to know too much about it. We do have to configure it. And so I'll skip right down here. We're gonna use online cover, which is a strategy for the exploration. And really there's multiple strategies. There's the epsilon greedy, there's bagging, there's Thompson sampling. These are all different variants of explore versus exploit. They have their own hyperparameters. Epsilon greedy has something called epsilon, and really this is the aggressiveness of which you will explore the non-winning or non-ideal variant. And number of arms, so this is number of models. So we have model 1 and then model 2. Policies is specific to the online cover. These are essentially nested or sub-policies that are used and then ensemble together to decide which variant to serve up, which model, which Bert model, which action to choose. All right, so we load that up. Oh, and the cool thing about multi-arm bandits is that you can actually add new model variants like throughout the life cycle. This is completely unheard of with the A/B test. Yeah, so you can't do this with an A/B test. So sometimes, for example, when I worked at like Netflix, I remember being placed into a bad test cell. And because I worked there, I could actually look it up and see which test cell that I was in. And I saw I was starting to get a bunch of things like romantic comedy sent to me randomly. They were exploring my, if you know, I would start to choose romantic comedies. And really, I just kept saying, no, no, no. But because it was a fixed test with A and B, they couldn't pull me from that test cell. With multi-arm bandits, they would slowly realize that that model wasn't working for me and would shift traffic to either the old model or some other model that better suited, and would then maximize the reward, which that case would be, yeah, so that would be me pressing play and watching more of the films. All right,
and
so here,
Chris, how do we penalize or reward in production when we don't know the real right class of input?
Yeah, so typically rewards would be longer form. So, you know, this is a fabricated case because we have the data, and so I'm just simulating this, but typically the reward is tied to some business metric. So at Netflix, for example, it would be, you know, plays or streams was the key metric. We could also, with something like recommendations, when you present the top 10, you would do 0 reward for the first 6. And if I chose number 7, 7 would get rewarded, but those first 6 would not get rewarded. So there's lots of content on recommendations. In this, I think I have a link to the blog post that actually talks specifically about recommendations. Yeah, the Amazon blog post on contextual multi-arm bandits. And that's actually training a recommendation model. And also there was a recent blog post by Stitch Fix based here in San Francisco. That's really cool, that talks about how they use these multi-arm bandits to choose the humans that are in the loop that are stylists for people who want Stitch Fix to recommend clothes and send them clothes to try on and potentially purchase or send back. But yeah, these are typically done offline. So we're doing the rewards online because we have the data, and yes, we just have so much time here, but that job runs offline, could join data from Redshift or from S3 or from wherever. All right, so let me jump down to the continuous training loop. This is just a bunch of code here. This is a massive notebook. This is one of the newer notebooks. We still have to split it up. Haven't gotten to that just yet. First time we demoed this was actually on Saturday, I believe. Okay, so here's the training loop. So this is simulating a continuous training loop. You know, this is something we would schedule as a pipeline, you know, component where we would, yeah, so either cron and then trigger this pipeline, or we could run it when new data comes in off of Kinesis into the S3 bucket. But yeah, basically looping over this. And so this is just gonna do it 10 times just to kind of put a finite. And we are going to get the rewards, which we have because we actually have the data. Yes, in this sort of made up scenario. We then publish the rewards out to S3 and then CloudWatch. We then ingest. And so now we are going to retrain the model. So every step through, so we're doing 10 loops, or we're doing one loop with like 10 iterations. Each iteration, we are going to retrain the model, test if the new model is better than the current model based on trying to minimize regret and maximize reward. And so this is where we're actually testing. This is actually comparing the regret. So we want the new model to have less regret than the current model. If that's the case, we then deploy it. And now that becomes the new model. And we deploy this in a blue-green manner so that there's no downtime. All right, and let's skip ahead to the results of this. And so keep in mind, Model 2 is much, much better. Was trained for 5 hours, whereas Model 1 was trained for 1 hour. And so we see that the Bandit actually chose in the long run to send more traffic to Model 2, which is a good sign. Let's keep digging and actually get some fun data science-y charts up here. This is a chart of the same data, basically. This is like the invocation. So showing you at first, it was exploring both Model 1, which is in blue, and then Model 2, which is orange. And then eventually, overall, it has chosen Model 2 for most of the iterations, or for these predictions. Okay, and then this is, so this is charting the action probability. So we see for the most part, the Bandit model learned that orange was best and was trying to exploit. And so here we see the overall probability here was 0.91 for Model 2 and then 0.59. So this is the probability that the Bandit will choose which model. Here's another variation here. So we see there was some initial exploration going on with Bert Model 1, then there was exploration going on with 2, and it started to like 2, but the Bandit then chose 1. It's still trying to explore, and then eventually really chooses 2 and starts to exploit that, still chooses 1 for a little bit, but then towards the end really goes in and hits 2 pretty hard. And then this is a quick peek at the sort of overall regret, or sorry, this is the reward, which is 1 minus the regret. And so here we see it kind of starts off where it doesn't really know, then it starts to explore, and the reward goes down, which this chart is not good. We actually want reward to be high. Then it starts to see good reward, but it starts to explore again, and the longer we run this, hopefully higher this would sort of level off. I've seen it level off around 0.8, 0.9, which is the ideal case. And so I think that's it. These are the DynamoDB tables that are involved, just in case you're wondering, a couple S3 buckets. And yeah, we then clean up the experiments, and that's it. So let me just finish off here with a quick review of this chart. And this is what we implemented. One line of code can actually create the Kinesis Firehose, the S3, the SageMaker training jobs, and the DynamoDB tables, which actually are not listed here. But pretty straightforward architecture, pretty cost efficient. And yeah, so with that, yes, are there any questions, Antje? We got about 5 minutes left.
Yeah, I know. Maybe just one out of curiosity. Somebody is asking if we know whether YouTube video recommendation engine uses a similar reinforcement learning model to recommend videos with a similar.
Oh, I'm sure it does. Yeah, yes. I don't know firsthand, but yeah, I'm sure it does.
All right, perfect. So yeah, should we do, so we had one more topic on the agenda, which is how to automate the whole process and to build up a pipeline. Do you want to just quickly maybe pull up that notebook? So we don't have to switch screens in the last 4 minutes. Just do the first one. Yeah, exactly. So, and I'll just maybe do the talk here, if you don't mind.
Yeah.
So basically, what we do have here as the last section is all those steps we've been doing now in basically pre-processing the data, training the model, deploying the model. How can we automate this in the next step? And as part of the AWS services, there's one service called step functions, which allow you to build this DAG, this is directed acyclic graph here basically, and execute different steps. And step functions also offers a data science SDK, which you can basically just pip install in a notebook. And it comes with templates, for example, training pipeline templates. And this is what we're using here. So we're basically just, pip installing here the step functions SDK, and we're setting up a couple of IAM policies, which basically just gives the service, permissions to access your data and spin up training jobs on SageMaker. So anything any service does has to have permission. So this is what we're setting up here. And then finally, we're having here a little bit of customization. So you can even do this with less code. But we're basically bringing in our processing script, which we've seen before, and we're uploading this to S3. So actually step functions has access to it. We're setting a couple of parameters here, specifying the input locations. And maybe just scroll down here to where we're building the actual script, setting all the hyperparameters for training, metrics, setting up the estimator object, and maybe set up pipeline with step functions. So we're pulling in a couple of components here, and you can see here from step functions, we're importing the training step, transform model step, endpoint creation, endpoint, etc. So we can basically now start building that pipeline with those components that are already known, and then just really customize taking the inputs we're providing. So going through all of those steps, processing, here's the first processing step. We're pulling in, pointing it to the processing script we've just uploaded, and pretty much the information we've done manually, defining the training step, defining the endpoint, model step, and then chaining it all together. And this creates this nice visual that we've seen. And then basically the execute here. And exactly, then we're calling here the pipeline. We're creating this training pipeline object, and then we can here render the graph. So you can see this visualized, and we call pipeline execute. And this kicks off basically the step functions execution. And as you can see here, it then goes through each of the steps and executes everything. And this will help us automate all of those manual steps. And even fun, you can then set triggers. So once you have this automated pipeline, and you don't necessarily have to pull up that crazy amount of code here. If anyone is interested, we set up a notebook here actually that triggers the training pipeline on new data that is coming into an S3 bucket. So we do this here in the sample notebook by uploading data to an S3 bucket, and the bucket is watched, and whenever new data is coming in, it will trigger the execution of this training pipeline. So and this, I guess, pretty much brings us to the end of today's session, literally on point. I think we answered many questions here in the chat already. Robert, I don't know how you normally do this. Feel free if people want to unmute themselves and maybe ask a question or give feedback, or keep sending them in the chat. I look if we have, is this code using step functions accessible? Yeah, definitely. It's all in the Git repo. So if you go to our GitHub repo link that we shared, you can find all the code examples there. So this is basically in the, I think it's 10, number 10 for automating for the pipelines.
Antje and Chris, thank you so much for your demo today. I'm so impressed that you were able to keep this up for 2 hours. I remained enthralled and excited the whole time. I'm even more impressed to hear that you've got an upcoming full day session going, which I think will be really exciting for people who want to get hands-on. We're here right at the hour. So Antje and Chris, do you have time to stay for a few more minutes if people have additional questions?
Sure.
All right, and Chris just shared in the chat, in case you're not on it, the upcoming workshop is free. I'll also make sure we put a link to that on the meetup page. So for these questions, if you'd like to answer them live, ask them first in the group chat, and then I will call on you to ask your question live. So unmute yourself and ask your question live. So who's got a question here in the chat? So Jim, I'm not sure what your real name is. That's what your short name is, Stijn. You've got a question about endpoints. Would you like to ask that? Oh, we might have lost you at the end of the hour, so I'll ask this one then. Does SageMaker support Grpc endpoints, for example, via Triton or TensorFlow serving?
Yeah. I put a response in here also.
Oh,
yeah,
you
SageMaker
right.
just uses. Great. Yeah, SageMaker just uses TensorFlow serving. It's an open source, like base image that uses TensorFlow serving, uses Torch Serve, which is a new project that was co-created with Amazon Web Services and Facebook/PyTorch community. Yeah, so we certainly do support Grpc, of course.
All right. And LKSA, you had a question about Bert's limitations, which I think would be relevant to a lot of people. Are you there to unmute and ask that?
Yeah, so my question was, is the 512 limit per sentence, or is it per training document, irrespective of the training document having many long or short sentences?
Yeah, so for that, let me try to pull this up here. Because I've seen a lot of talk about Bert longer than 512 and different ways to do this. So if you Google around for Bert for long text, so we have not had this problem because number one, we are not doing question answer. So we are just using text classification. So we're not the best people to answer this. I would definitely tune in to the Thomas Wolfe, and I'm going to tune in. And if nobody asks this question, I'm going to ask it. But yeah, there's like lots of
to begin with that, maybe you can clarify what is that 512 limit? Is that characters or words or something else?
Yeah, it's definitely tokens, which are roughly words. Some words get broken up into different tokens. The other thing is Bert uses something called word piece, I think it's called.
Yeah, word piece embedding.
Yep.
Yeah.
And so there'll be some.
Yeah, but my primary question was, I know it's the tokens, 512 words or 512 tokens, but is that per sentence within a document, or is it per a document, irrespective of the number of sentences in it?
Right, and yeah, if you're passing in a complete document and trying to predict whether or not a answer, or if you have something larger than 512, like a paragraph that's larger than 512, and then you want to predict if there's a sentence that follows that paragraph. Yeah, that's an area I would assume, based on my understanding, that paragraph cannot have more than 512. That's the limit, and it will truncate.
Yeah, that's my understanding too, that if you're doing a classification task or a next sentence prediction task, any of these tasks is per document, irrespective of the length of the sentences within the document.
Yeah.
And one more interesting thing that we found was, when you have these long sentences or long documents, you can somehow trim it to retain context by taking maybe first and last sentences of each paragraph, right?
Gotcha.
So empirically, that's what seemed to work. I don't know why, but yeah.
That seems really interesting. I would, if you have links to that, I would. I'd love to hear more about that. I know a lot of people would. I think the standard way to do prediction on longer documents, if you're doing next sentence prediction, is to truncate the start. So you've got that natural continuation.
This was for classification.
But it seems like it seems like a smart strategy. There's theories about why you put the most important information at the start of a paragraph. So I'd be curious to see those results if you can share them with the group.
This was for a client, so probably what I'll do is I'll recode this on maybe the BBC news data set or something, and probably throw a GitHub out there and probably share it in the next session.
Sounds great.
Awesome.
Thanks. Yep.
Right. What other questions do we have here? Jali Song, do you have a question?
Yes, I just curious about, maybe not quite related, but I'm curious about if the distilled bird perform relatively the same with the normal bird.
Yeah. So here's the paper. I'll post it in the chat there. And they claim 97, let me zoom in here. Oh, zoom in. 97% of the natural language understanding capabilities. And it's
okay, how about your experiment, your exploration? I mean,
yeah, because we wanted to run part of this in the notebook, we actually had to use Distilbert for the size. To be perfectly honest, I don't think, Antje, we've actually gone back and compared Bert with Distilbert. Like, we were seeing really good performance with just Distilbert, so we just stuck with it. Yeah, okay. I don't have much more info there. It's definitely faster, by the way, because we had one other team member who was seeing multiple second latencies when he was doing predictions up to 10 seconds. And we never saw that. Ours were always millisecond predictions. Yep.
Okay, thank you.
And I highly recommend anyone who's interested in distilled models to come to our meetups in October and November. So Thomas Wolf, one of the authors of this paper here, will be our speaker in October. And then Magana Ravikumar will be speaking in November about strategies for how she has been distilling models while trying to optimize the accuracy. So it's a really interesting topic at the moment. That's a great question.
How do we find the links to Thomas Wolf's and Ravi's meetings on Eventbrite?
Oh, I mean, they're at the meetup. So the same website that you signed up for this one.
Got it.
You'll see upcoming events there.
Thanks.
Okay, thank you.
I'll drop another link into the chat window here as well.
Yes, I want to point out one thing actually that you should keep an eye on when you're using Bert. Me and Antje hit this the hard way, and this just popped into my head. When you're using Hugging Face, it is pulling from the Hugging Face service at times. This is kind of an advanced topic, but this does apply when you're working in the cloud. If you want to achieve true network isolation, if you have security constraints or you don't want to depend on an external service, keep in mind that very simple calls like, does it load pre-trained? So this call right here actually calls out and pulls this model from Hugging Face. And they use, so they use AWS, they have S3. And one thing we found was if there's any network partitions or if Hugging Face goes down, I've never seen it go down, but if you want true network isolation and want these training jobs to run no matter what, make sure that you potentially pull this down and put it in your own S3 bucket or burn it into your own Docker image. This is a potential single point of failure for your training jobs. And so this is more on high availability training. Typically people don't think about high availability in terms of batch jobs and offline training, but with machine learning being so critical these days, you really want to make sure that you don't depend on these third-party resources. It's the same argument,
That's
by the way.
That's some great advice. I'm using Distilbert at the moment, and I did not realize that I would be. I would have that dependency if Hugging Face goes down.
Yeah, and it's the same argument why you would want to do pip installs and burn those into your Docker image. And you could deploy your own Docker image with SageMaker, by the way. There's no limitation there. But if and actually I've had this problem way more. I mean, I've never had a problem with pulling these down from Hugging Face, but I have had problems where PyPy is down or there's something, there's a HTTPS proxy issue, and my training job didn't start because I couldn't run a pip install TensorFlow. So yeah, keep that in mind. The way to test it within SageMaker is to check the box or pass in the, I think it's network isolation mode. You would set that equal to true. And that will then just cut off all access to the internet, and you'll find out right away what you depend on and what you don't.
That's good advice. Good software development practices in general
Yeah.
as well. If you're creating images or containers, is to have them as contained as possible. That's why we have these technologies.
Yes,
no pun intended. Containers being contained.
Yeah, yeah. There was more than one Netflix outage because of this exact thing. I mean, not specifically PyPy, not like Hugging Face didn't even like exist back then, but yeah, I was at Netflix multiple times. We were depending on external services or even different microservices within Netflix. And if we were trying to auto scale up super quickly because it was Christmas Day and the other team didn't know, we basically DDoSed that other team and then we couldn't start up. And so it's always good to isolate. Yep.
And of course it was during a holiday, right?
Christmas, yeah, for sure.
Any more questions here? Ashad, thanks for sharing that link to more about the maximum input size as well. Any other questions for our presenters? Well, I think we're good for today then. Let's thank our presenters again for taking the time today. And if you do find you have any questions later, we'll share that link so you can come to their free all day workshop. Is that this Saturday or is that a later date?
We just did one Saturday. This past Saturday.
Saturday just gone. Oh wow. Okay.
Yeah, but we do them every month. So the next one will be 4 weeks from yesterday. Yep. So I think it's.
Hey, can we get a recording? I had to join late because of work meetings.
Yeah, we made a recording. We'll as with all our meetups, we'll get together afterwards and see if it's going to be okay for all our organizations to release this recording.
Okay.
Please stay tuned. We'll send out an announcement if we do.
Sure.
Great. Yeah. Thanks, everyone.
Thanks for having us.
All right. Thanks, Antje and Chris. This is really good. Really appreciate it.
Awesome.
Thanks all.